Hello, I'm Nolan Chan, and I will present how we tackle new challenges in optics testing using wavefront sensors. So I'll start with a few words about our company, and then I'll describe our technology, and finally I will give an example of application using one of our systems. So Phasics is a French company that was created in 2003. Our core expertise is providing wavefront testing solutions from 190 nanometers to 14 microns. Our systems goes from the single wavefront sensor and the software that can be integrated in your system to the complete test bench or complete test machine that we have, for example, here, which is called Calino MTF. We can also provide interferometers, that is like Calino multi-wave, that is here. And we can provide, of course, in-between solutions like the R-Cube, which is an illumination module so that you can couple it easily with a wavefront sensor for compact wavefront testing solution inside your system. So our technology, QWLSI, is based on two main components. One is the diffractive grating that we can also call modified Hartmann mask, and the other one is a sensor that can be from different technologies, like for example CCD, CMOS, InGaAs, etc. So what happens when you send a beam inside? So the incident light will go inside the sensor. It will first encounter the diffractive grating that will create the four replicas of the beam, which are the plus and minus one order of diffraction along the x and y axis. These four orders of diffraction will then propagate until they reach the sensor a few millimeters away. And on the sensor, they will interfere with each other, creating an interference pattern, which is a 2D sine function that you can see here. So this is the raw image that you get from the sensor. And what we do to obtain the phase gradient and then the phase is that we analyze the frequency modulation of this pattern. If the incident light is completely flat wavefront or collimated, it will create a periodic 2D sine function. But if there are distortions, there will be local modulations of the phase, at least of the 2D sine function. So why we use this technology? So there are several advantages to it. The first one is the high resolution. So we only need a couple, like 3 or 4 detector pixels to obtain one measurement points. So this is to be compared to a Shack-Hartmann sensor that typically needs between 8 and 16 measurement points. The second one is the large dynamic range of the system. We can measure roughly up to, or even more with some systems, 500 microns peak to valley of aberrations. But we can also handle high NA. So this is why this type of measurement setup is possible. So if you want to test a focusing optics, we can directly work with diverging beams. So it means that you don't need here to add the aberrations of a relay lens or to align a relay optics to make measurements of a focusing system. So this is what we use typically in our Calino MTF solution that I will present later on. The third advantage is the achromaticity of the system. So we can make analysis and measurements with the same accuracy with different wavelengths. So it means that you can really use the wavefront sensor to characterize the chromatic effect or the chromatic behavior of your optics on this test. So this is also particularly useful when you want to characterize a lens system. Let's take an example of application now. So if you look at smartphone industry where you need to get the best camera modules, the best lenses to get the best images and best image quality, or if you look at the autonomous cars, so in automotive industry where you need to see as clearly as possible the environment so that the computer can make the right decision, we can translate the technical issues into two parts. So one in terms of functionalities, because they need to make sure that the lenses give the same image or has the same image quality for different wavelengths in the visible spectrum. So colors, for example, like red, green, blue. But you also need to be sure that the image has the same quality in the middle of the sensor, so on the middle of the image or on the edges of the image. So you need to make some verification on and off axis. But you also need a really high precision and really high repeatability in order to separate a good and a bad lens at this level of quality. It also translates in terms of specifications in, for example, high NA. So the lenses need to get into high NAs to cope with the resolution of the camera pixels, of course, but also to have a compact system. This is also linked to the large different angle here that are larger and larger to have more compact system as well. And for autonomous cars, for example, it is also cope with the wide field of view in order to see as much as possible with as few as possible camera modules. And for this, Phasics has developed Kelio MTF, which is an integrated test machine, an automatic test machine for these typical lenses. So how it works is that you just place inside the lens that you want to characterize. You don't need to input any data. So the system can also be used as a benchmarking system and not only a measurement characterizing a quality control system. And the output that we have are typically as large as possible. So since it's based on a wavefront sensor, we of course output the wavefront error and the Zernike aberrations that help you understand typically MTF results so that you know where the aberrations or where the drop in MTF can come from. We also output, of course, radiometric or photometric information with relative illumination and also geometric parameters. So for example, effective focal length, distortion, field curvature, etc. So this is really used so that you can make measurements of as much parameters as possible in all of the different configurations that you want. So we test, of course, on and off axis. We test at different wavelengths that you can choose, up to 8 in the middle, but also in the near infrared, which is quite trendy at the moment. We do all this with a high accuracy, so we have here 0.5% MTF precision on axis, but it goes only up to 0.7 for the whole field of view. The system is completely automatic, so you don't need to align anything, you don't need to be there for the measurement. You can test at different azimuth, for example, and the outputs, all the outputs can be directly compared to a design results, because we give the result in the exact same plane. So we made measurements to, of course, make sure that the quality of our system was able to cope with the quality of the lenses on the market. So we made measurements of trueness, so to compare directly with Zemax of a system that can be easily simulated and accurately simulated. So we see here field curvature comparison with Zemax, MTF comparison with Zemax. You can see that you really have a good fit of the two results. The second is, of course, in terms of repeatability. We made measurements of all the different parameters, and we can see that I mentioned before the MTF repeatability on the whole field of view that is here, but you can also notice that in terms of OPD repeatability, so optical path difference, we are really in the nanometric range in terms of repeatability. And this can be used for testing, for example, similar objectives and determine whether they're okay or not good or different. And we can see here a practical case where we take an autonomous lens, autonomous car lens, automotive lens, sorry, and you can see that even though on axis they have really quite similar specifications, on the edge they can be quite different. And we also output the aberrations to identify where it's coming from. So we also make, of course, measurements for the chromaticity or the chromatic impact on the lens, and we can see that for the different aberrations that the behavior can be different for these lenses. So overall, at Phasics, we make systems that can make, of course, measurements in transmission to measure transmitted wavefront error, in reflection for the reflected wavefront errors. As I mentioned in the beginning of this video, we make also interferometers typically. We measure, of course, the MTF and the PSF on and off axis. So we can work in different kinds of configurations, so single pass, double pass, point to point, infinite to infinite. And we have also, in terms of versatility, whole different levels of integration. So from standard wavefront sensors to custom optical test benches. If you have any questions, don't hesitate to contact us. We'll be glad to help. So this is the end of the video. Thanks for watching and see you next time.